are related to transformations. And to introduce the symmetry, and define symmetry, maybe better, is to define transformation. And then the symmetry of some object means invariance under transformations. I gave to you a simple example with this circle, and this actually allows to clarify all the issues related to the symmetries. So what is this X we will discuss? This X is Lagrangian of the theory. It can be a question of motion. Or it can be just state of our system. So we can talk about symmetry of the state, symmetry of the question of motion, and symmetry of Lagrangian. And these two are not necessarily the same, they are not coinciding in some cases. So mostly we will focus on the symmetry of Lagrangian. Or Hamiltonian. So our Lagrangian in general is some functional which depends on the fields and coordinates. So in general we can transform coordinates and we can transform the fields, or we can introduce kind of combined transformations, fields and coordinates. So for this we are introducing transformation law. So we transform f to f prime, x to x prime, and the transformation law gives us relation between original fields and transformed and original coordinates and transformed coordinates. So this is transformation law. Now, the invariance means the following, as we have already discussed before. We can start with this Lagrangian and insert f and x according to these transformation laws. So what we will get, gf is functional of f prime, gx functional of x in general. And now, if after transformations, after studying this, we show that that can be reduced to the same form of the Lagrangian, but in terms of, I think it should be prime, in the same new coordinates and fields, then we are saying that Lagrangian is invariant. Now, the symmetry of Lagrangian leads to various physical consequences. And these physical consequences depend on the type of the symmetry. type of the symmetry. And different symmetries have different physical consequences. And very often, Lagrangian is invariant under several symmetries. So what are these consequences in general? Symmetries provide for us classification of particles. And we already met this before. The symmetries, certain symmetries lead to conservation law. Or selection rules. Symmetries lead to equalities or relation between masses. Like equalities or approximate equalities of proton and neutron mass, or qualities of the masses of pi plus, pi minus, and pi zero. The symmetries provide certain properties of the amplitudes and probabilities. And finally, the symmetries give relations between different amplitudes and probabilities of different processes. Which means that no need to compute probabilities for all the processes. If you know the symmetry, that gives you this connection. It's enough to compute, say, one amplitude of probability, and then using symmetry you can find out other probabilities and amplitudes. Here also you may find some properties of the amplitudes, dependence on kinematical parameters, for instance, on spins, on momenta, and I will give you examples. When you can know this already in advance without explicit computations, just using symmetry, you can say what should be dependence of this amplitude or probability on momentum, on a spin. What I will do now, and we have already discussed different symmetries. Symmetries may be of different form. You may just simply change the sign, or multiply your field by some phase, or change the coordinates. So symmetries can be very different, and you can try even to explore. So it's an interesting problem. You can introduce by yourself or invent some symmetry. So why not to try if I do this transformation? So if it has some sense or not. So this is a common problem. So opposite problem is that you have already some Lagrangian, and then you can explore what are symmetries of this Lagrangian. What I will do now, I will introduce, again, general features of the symmetries at quantum level, which of course has some correspondence to what we introduced at classical level. But at quantum level, everything becomes very simple, surprisingly, very elegant. And one can extract the symmetry properties or consequences of the symmetries at quantum level very easily. So let me recall, first of all, that in quantum field theory, everything is made of operators, right? So this is how we build up, especially when we make a secondary quantization. So everything is determined in terms of the operators of the fields, or even more precisely, operators of production or annihilation of different particles, right? So this is A dagger, B dagger, probably did this, right, in quantum field theory course. So everything is constructed out of these operators. So operators. Of fields. And also physical quantities are constructed in terms of operators of the fields, right? I hope you did this inside. And vacuum state. So these are the main elements. We introduce vacuum state as the state with the lowest energy of our system. And then other states can be produced. Let me put here. And this is operator, which is made of this A dagger, A, B dagger, B. So then all the states can be produced by acting or by operator of the field onto this vacuum state. So essentially this is a sketch of quantum field theory, and then kind of interaction between different elements are reduced to commutation or anti-commutation relations between operators, right? So what is important that also transformations at quantum level becomes operators. So also transformations becomes operators made of fields. And they can be expressed in terms of fields. And eventually in terms of these operators of production and annihilation of the particles. Let me just write, and so this U becomes the function. Yeah?
Here, do we use dagger or?
Well, so this is production, right? So dagger. But usually just to make things, dagger means production, right? So that's.
But phi also contains the dagger inside.
Yeah, so then only, some of this will just annihilate, right? So you are saying. But if you want to produce, of course, we need to pick up corresponding A dagger and B dagger. So, transformations become the operators. Well, let me use this notation. I use operator. Sorry, this is the transformation. So let's take operator. Any operator. It can be field operator, it can be some physical quantity expressed in terms of operators of production or annihilation. Then transformation of this operator under this U is given by U operator, and here is U minus 1. And this is U minus 1 is inverse transformation. So, which means that U minus 1 is unit. So this is a general transformation law at quantum level. So if U is operator of transformation, then transformation of a given operator is done in this way. Now there is a correspondence to what we have in the case of classical physics. And I will show you this later. I will not provide some kind of a general proof for this. So this is the way how we are defining transformation of operators. So and again, amazingly, that everything is eventually depending on this A dagger, and B, and so this actually, the result of this transformation essentially reduced to commutation or anti-commutation of this A and B. Now, this is operator, yeah?
Is it this fact that we can express everything in terms A and B, is it like an axiom that we should put, or so is it an axiom that we construct all our theory on it, or
yeah, this is secondary quantization. I don't want to really, so you need to ask this question to Giovanni, right? So, okay.
Yeah.
How this is built and why it is built in this way. And this corresponds actually to usual quantum mechanics, if you want, how we build that. So you can prove this. You first start from quantum mechanics, usual quantum mechanics, which is clear. But then you do secondary quantization, right? And you express everything in terms of these operators. And then you introduce commutation or anti-commutation relations between these operators. And then you can actually establish correspondence of what you had in quantum mechanics, of just simple quantum theory, and a theory with secondary quantization. Now, I just introduced a general operator, O, but I can use this field, and therefore the field, so I can use O, which is our field, and therefore the transformations of the fields are given by the same law. Everything becomes very universal and very simple in a sense. So I will often use unitary transformations. And for unitary transformation, U dagger is unit matrix. And therefore, U minus 1 is a U dagger. Now I have introduced vacuum state, how vacuum state transforms. Actually, this is interesting question, because again, remember that vacuum state is determined as the state with the lowest energy. So it's not necessarily empty, and so we can talk also about transformations of vacuum. So vacuum can contain fields, you know. So. Now the transformation of vacuum state is defined in the following way. Transformed vacuum is given by U acting on vacuum. And I will show later that this is consistent definition, determination of transformation of vacuum. So, if vacuum is symmetric, or invariant under transformation, what we will have, U acting on vacuum gives again vacuum. So we can write this also in the form that inverse transformation acting on vacuum again gives vacuum state. So it's clear that these two are related. I just multiply by U minus 1 on the left hand side, and I will get a second equation. So now let us discuss transformations of state. So this is transformation of vacuum. Now transformations of general state. So let's take state F prime. And this is built up by acting of F. So let me just skip here dagger, because otherwise it will be messy. I just put it here, F, which also contains production operator. So I create this state by acting of the corresponding field operator on vacuum. Right, so this is how we can construct the states. Now I know how this operator is transformed, and therefore I'll write this as U, F, U minus 1, acting on vacuum. Right? So this is what is my F prime. Now, and this is important, if vacuum is invariant, then this is again vacuum state, and therefore what I will have here, U, F on vacuum, and this is U acting on F. So this is the law of transformation of general state. F prime equals U acting on F. Oh, vacuum. So, sorry, F prime. Correct. Okay? So this is the law of transformation of general state. And here you see consistency with what we introduced for vacuum, because vacuum is one of the states. Clear?
So we can always transform the observables, but transform the states, we need an invariant vacuum.
So the point is that this is not necessary, because sometimes vacuum is not invariant, and actually when we are talking about spontaneous symmetry breaking, this is precisely the case when vacuum is not invariant under transformation, and then everything is changing. So that is referred to the case when vacuum is invariant. And transformations of the fields as it was introduced in general. Field operators. So in the case of spontaneous symmetry breaking, this is not correct. So vacuum changes. This is actually how the symmetry is broken in the standard model. And maybe some other symmetries also are broken in this way. Now, invariance of operators. Invariance means that transformed operator coincide with the original one, or explicitly U or U minus 1 equals original operator, right? So this is the symmetry or invariance of operator at quantum level. Or this can be written as U O equals U, which means that invariance means that we have commutation, that operator commutes with operator of transformation. So this is how invariance is expressed at quantum level. Commutation of a given operator with operator of transformation. This is invariance at quantum level. simple, right, and elegant. You know, it's not like you are inserting something. You just should check this. So, since I said that in most of the part of our lectures I will discuss invariance of Lagrangian, which is operator, right? And therefore, invariance of Lagrangian is expressed as commutation of Lagrangian of Hamiltonian, commutation with operator of transformation. So this is invariance of Lagrangian. So this kind of general formalism allows us to see what are the consequences of the symmetries I mentioned already. Okay? And first let me discuss relations between matrix elements. I said that one of the consequences of the symmetries is relation between matrix elements. And then we put the consequences of symmetries. So relations between matrix elements. So suppose Lagrangian is invariant with respect to transformation U. Transformation described by the operator U. In most of the cases, this leads to invariance of S matrix operator. So an S matrix operator is introduced as a time ordering exponent of integral of the Lagrangian. Okay? So invariance means that U acting on S, U minus 1, is S. So this is invariance. Of S. So let us consider matrix element between the states F, S, and I. So between F and I, and I put here this S operator. So what we can do, and suppose for simplicity I will use here a unitary operator, I can insert here one which is U dagger U, and here is one which is U dagger U here. So what I will get is F U dagger U S U dagger U I. Right, these are just one, and this is one. And then, what is here can be written as F prime. Now this, let me put here, that's F prime better. So here is I prime. And now this, if I have invariance, is S. Right? This is invariance. So if S invariant, then my original matrix element is reduced to this expression. And this is S F prime I prime. So, which means that this if S operator is invariant under transformation, then all matrix elements between the states which are related by symmetry transformations are equal. It's very powerful, right? Because again, you compute just one matrix element, And then you can find all other matrix elements by just using the symmetry argument. So let me write this. So the amplitudes of transitions between states related to symmetry transformations are equal. So this is power of the symmetry. If you establish that your Lagrangian is invariant under certain transformations, it gives you this very important tool. You can find the matrix elements in this way. So related to this is the proof of equality of masses as a consequence of symmetry. So here's equality of matrix elements of transitions. Now, equality of masses. As a consequence of symmetry. So mass can be determined as matrix element of this type. We have the state I, and Hamiltonian. Hamiltonian is operator of energy. And if you go in the rest frame, that gives us the mass of the state I. Now the same argument we put here, this one, which is U dagger U, and also here. And if Hamiltonian is invariant, so what we will get is the following: I, U, H, so U dagger U, I, and if U acting on the state I gives me the state F, then I will find that I will have here F, I, H, F, and this is the mass of state F. So, conclusion is that all the states which are connected by symmetry transformation have the same mass. So the states which are connected by symmetry transformation form multiplets, which I have discussed already, like isospin doublet when proton and neutron, they can be transformed one into another by doing transformation. And so this means that all these particles of the states which are connected by symmetry transformations form multiplets. Transformed under certain representation of symmetry group, and therefore all the components of multiplet should have equal masses. Like pines, pi plus, pi minus, pi zero for triplet, and in the symmetry limit, the masses of these particles are equal. So if you have some multiplet in which you have different masses, it means that symmetry is broken somehow. Like we know that octet of mesons, which contains apart from pines also k mesons, the atomism, which have different masses from pions, this signifies that there is some breaking of the symmetry. That's some mechanism of breaking of the symmetry. Symmetry is not exact. Another important consequence of the symmetry, as I said, is classification of particles and conservation law. So, in general, and I mentioned already, generators of symmetry transformations can be identified with certain physical quantities. So example was, for instance, isospin. On the third projection of the isospin, that was actually the generator of SU2 symmetry group, which is associated to isospin. And at the same time, this third projection of isospin is physical quantity. The same we also discussed for strangeness in the context of SU3 group. So what happens that there are some generators which are diagonal. They play a crucial role here. So certain generators have the feature that acting on a state, it gives just some number and the same state. Like again, we discussed this isospin third projection, which is given by sigma 3 Pauli matrix. It is diagonal, and it actually satisfies this property. And here the B is, in the case of proton and neutron, 1/2 and -1/2. Remember, so you may have this type of the generators of the group. So this equation can be considered as a question for eigenstates and eigenvalues of operator Q, right? So B is eigenvalue of this operator for the state I. So according to quantum mechanics, Bi can be used as this is characteristic of the state I. And it can be used as quantum number, which describe the state I. Again, come back to example with isospin. We have this with B 1/2 and -1/2 for proton and neutron, and this can be used as a characteristic of proton and neutron, the third projection of isospin. So we can use then B to classify our particles. Suppose we have another state, F, which has another eigenvalue, Bf, which characterized state F. Now, if Hamiltonian, or Lagrangian, if Hamiltonian is invariant under transformations given by Q, this means that HQ minus QH is 0 and commutes with Q, right? So Hamiltonian is invariant. So let's take this equality in between states I and F. So let us consider the following. Take F, and then here HQ minus QH I equals 0, right? So because this is 0, I take this 0 in between F and I state, and I have this equality, right? Now, let me consider Q to be Hermitian. And this is needed to identify this with some quantities, physical quantities, because then B is real in this case. So that's important. In this case, we can, because we don't know what is this complex physical quantities, electric charge and so on. Therefore, we can get from this equality the following. That's this one. So this is attached to F state, and we can write this as F Q dagger because that is Hermitian, and that will give for me BF F. Okay? Now the second term, in the second term I act by this Q on I because Q is attached to I state, and what I will get, Q acting on I gives to me B I in state I. Therefore, this equality can be written in the following way. So we have here two terms, right? So that can be written as BF FHA minus BI. But what happens, we have the same element, FHA. Right? Agree? I can explain more. And this is 0. So two terms. In this one, I'm acting by Q on I, Q on F because it is attached to F, right? So on this side. This I act on I get these results. And so I can rewrite this equation as BF minus BI FHI equals 0. And from here I find that this matrix element is non-zero only if BF equals BI. So, which means that I can talk about conservation of quantum number B. This is conservation. Of B. So that quantum number B in initial state should be equal to quantum number in final state or vice versa. Okay? So, and I'm arriving actually to this equality. So only those matrix elements are non-zero for which I have a quality of B quantum number in final and initial state, and B should be a total quantum number of final state or initial states, not because in initial and final state I may have several particles, and therefore what matters is the total quantum number. So these are total quantum numbers. Which characterize initial and final state. Okay? So this is general consideration, and I think it will be enough for the rest. I will not repeat this type of analysis for each individual symmetry. I'll just refer to this first part. Okay, you can check for specific symmetries how it works. And now we will go to parity. Again, in spite of the fact that this is very simple symmetry, it has extremely deep and important consequences. And maybe I should first write that the way we will consider different symmetries is the following. First, we will define symmetry or define transformation. Second, check invariance. With respect to these transformations and invariance of, usually we'll talk about Lagrangian. And the third, find physical consequences. So, common question is why we introduce transformations in this way or not in another way, which is important question. So I will show you I will introduce various transformations. And again, why in this way? Why not in another way? First of all, you can try any transformations you like, you want, and to check finally if your Lagrangian is invariant or not. And it has some sense. But what we'll discuss transformations, because you may introduce transformations and your Lagrangian is not invariant. Okay, so then you should try something else. Then in some cases the transformations of different type looks different, but they can be reduced one to another. And there are some physical motivations to introduce transformations in this way or in another way. So that I will underline in each of the cases. Okay? So, parity. Some symmetry, or symmetry of Lagrangian, which we will discuss, and we need to introduce transformations. So what are transformations? X go to minus X, Y go to minus Y, Z go to minus Z, or you can say this R go to minus R. And we do not transform time. So this is transformation of coordinates. So actually this is example where we have transformation in both coordinates and the fields. So this is the way we are transforming the coordinates. These transformations are equivalent to change the sign of one of the coordinates. So for instance, Z go to minus Z, and you can do rotation in X y plane. And you can reproduce the same. So it's enough just from physical point of view, it is enough to consider just reflection. So left go to right, so just reflection with respect to z, for instance. Now, how other variables are transformed? P, momentum, go to minus P. Energy doesn't transform. Now, angular momentum, this is important. This is important point. So how the angular momentum is transformed and speed? Who knows?
It's minus.
Hmm? So this is vector, right? Or what? So why it doesn't transform?
And R.
So that's because it is vector product of R and P, right? And since both change the sign, then the product, vector product, doesn't change the sign. So this is formal. But from physics point of view, L, or direction of L, is introduced for our convenience, right? Remember this. Actually, that will be important when we'll discuss the parity violation and many other things, actually. So, actually what happens, what angular momentum characterizes is some rotation, right? So, it's something like this. We have rotation. And say the plane which is orthogonal to the blackboard. And then we are saying, for convenience, to have some kind of, at least to describe that this rotation occurs in this way, we introduce vector. And we are saying that if rotation go from left to right, then we characterize this by L, which is directed along the axis Z. So let me put here Y, X, and if rotation proceeds from axis Y to axis X, then we direct L along Z. But again, this is convenient. This is our convenience. Now, suppose we do P transformation. And under P transformation, all the axes change, right? So X will go into this. No, sorry, this is Y. Now X go to this. And after P and Z go into this direction. And we have this rotation. So I transform coordinates. Rotation is in the plane. In this transformed frame, so if you are sitting here, you just should turn your down. What you will have again, a rotation from Y to X. And therefore you are saying that, oh, then my vector L should be along the axis Z, right, in this way. And so in both cases, your L will be along Z, and in this sense it doesn't change, because you are just, you sleep and you wake up and you see in other frame, but again your L will be in the same direction, Z. So what is crucial, you do reflection, however you do not change rotation, it still occurs in the plane which is orthogonal to Z. So, and you see this rotation in the same way if you are looking from up or from down. Okay? So this is kind of, if you want, physical argument. So here is what formal stuff, so you have this definition as vector product. So in spite of the fact that you change coordinates, change the sign of coordinates, you still have your L directed along axis Z. And this is again because you do reflection. However, rotation occurs in orthogonal frame, and it doesn't change if you look from up or from down. Now, other characteristics important for us are currents. So how currents are transformed? For current, is transformed in the following way. You have 0 vectorial component of current, and under P transformation, 0 component doesn't change like energy, right? And vector components of the currents change the sign. Now we need to define how the fields are transformed. You see, every time we need to define everything, transformations. Then we define completely the transformation, then we should check if our Lagrangian is invariant or not. So the fields. How scalar field is transformed? We have f, which is the function of x and t. And under P transformations, they transform to the fp, xp, and t. P, I will do this just once, but then I will skip these intermediate steps and explanatory steps for other symmetries. And what is this transformed field with transformed coordinates? That can be written as f minus x t, but in general I can put here some coefficient, some factor. Let me put this as f, as eta p. So if we apply P transformation twice, so make P transformation of this, then what I will get eta P squared f x t. So, and if I do twice transformation, so inversion once and sine, I should come to the same state. So that should be f x t, which means that eta p is plus or minus 1. So this parameter eta is called parity. And for scalar field, it can have the value plus 1, and in this case, we call the corresponding scalar as scalar. So eta p equals 1 scalar. And eta p equals minus 1 pseudoscalar. You can check that the simplest Lagrangian for scalar fields is invariant under these transformations, under P transformations. So if you take Lagrangian in the form 1 or 2 d mu f minus m square over 2 f square. So that's the simplest Lagrangian for free scalar field. It is invariant under P transformation. So you can insert these coordinates and f in terms of transformed, and you will get it. It will be the same. The one subtle thing, then when you do just one P transformation, you change here, you will get here minus x and t. But appearance of minus sign here in arguments of this f doesn't play physical role, because eventually you are doing integration of your Lagrangian over whole space. So you do this. And if you change coordinate in symmetric ways, say from minus infinity to plus infinity, so you can just change the integration and absorb this minus sign which is staying here under P transformations. And of course, appearance of eta doesn't play, so it should be here, doesn't play if it is complex field. So if it's real, there is no things dagger here. So an appearance minus here doesn't change anything because you have square of the fields everywhere. So which means that this Lagrangian is invariant under P transformations. Questions? Now, how fermionic field is transformed? Well, amazing that just this, plus and minus sign play crucial role. There are many physical consequences of existence. It's not a joke, but so what's the point? You have just minus somewhere. All right, it's extremely important. Now, how fermionic field is transformed? Under P transformation. So we have again x go to minus x, and transformed field psi p is given by xt, and I will not I can put here, but it doesn't play any role, plus or minus here. Sorry, still let me put psi go to psi t under P transformations. And this psi p for fermionic field is given in general by this minus t. And in general, I can put here 4 by 4 matrix. So since psi are 4 component object, then in general I can put here B. I hope you studied this somewhere, right? So I will be very brief and not repeat too much. So what is this B, which is actually important? So how we can fix this B? And one important thing, that P transformation should not change spin, right? Because we have already discussed this. Under P transformation, angular momentum and also spin do not change. So B should be introduced in such a way that it doesn't act on spin variables. So this is by spinor, and we have in spinorial representation two spinors, right? So, and what this B should not, it should not change components within these spinors. This means that in spinorial representation, B can be either unit matrix or it can be the matrix gamma 0, which is given by in this representation. And this is 2 by 2, each of these elements in this matrix. Now, how to select between unit matrix and gamma 0? Tell me, since you already did this.
It's the Weyl basis of all the characteristics.
What?
It's either the Weyl basis, if you choose it like this.
No, in any case, I can choose some other basis and still I have in spinorial, because this is clear that then I need to define this in different way. So in this representation, it's clear that because I have plus 1/2 minus 1/2 in one kind of doublet and another doublet. So that's easy to see that this doesn't change the spin variables. So how to select between B and gamma 0? Yeah.
We know that maybe the simplest fermionic field is Dirac field, Dirac Lagrangian.
Yeah, so we are discussing Dirac field, Dirac Lagrangian, and
so we need to choose the one which is make it invariant.
you see, you are kind of so you need. This is a different way because you're already assuming that this is invariant, right? So usually what we are doing, we first introduce transformation and then check if Lagrangian is invariant or not. Yes, of course, if you assume that it is invariant then. So there are different ways, and again, you can introduce your transformations in trying to some different way. It's okay. You can try to see what will happen. So we are using kind of physics arguments, and the physics arguments are the following. So current, we know how current is transformed under P transformation. So zero component doesn't transform, and vectorial components change the sign. So the current is given by psi, gamma mu psi. And what we should have to have kind of consistency everywhere, under P transformation, gamma 0 should go to gamma 0, and gamma vectorial should go to minus. Sorry, J vectorial, right? That's how current should be transformed. And then if you use unit matrix, it's obvious that nothing will change, right? So if you put your unit matrix, it doesn't change. And therefore, the unit matrix will not give this type of the transformations. Gamma 0 is precisely what you need, because if you put gamma 0 and gamma 0 here when you insert this, what you will have is the following. So gamma 0 anti-commute with vectorial components, and they will have opposite sign, and therefore it will reproduce this. And gamma 0 multiplied by gamma 0 is 1, so you will not change nothing in a 0 component of the current. So that's clear from this that you need to take gamma 0. And then you can check that your equation of motion, Dirac equation, is invariant under this transformation, and also Lagrangian is invariant. Now, for electromagnetic field, that's kind of 4 vector, and therefore for electromagnetic field, we do not change under P transformation 0 component, and we do change vectorial components. This is for vector fields. Okay. You can try again some other transformation, but we define this P transformation in such a way, and then check what are the consequences. You can also use this, again, you can use, for instance, Maxwell equation and argue that, again, due to covariance, since you have this type of the transformation, so for scalar fermion fields, you should introduce this transformation of vector fields. Now, for fermionic fields, we do not introduce parity. Remember? So for scalar field, we introduce parity. And for fermionic fields, we do not introduce parity. To a large extent, that fermionic fields also always appear in pairs in our Lagrangian, and therefore, even if you introduce parity, it doesn't play any physical role. In contrast, scalar fields can appear in Lagrangian as, say, scalar field Q in the third power. Okay, therefore that will play, the parity will play the role. Now for vector fields again, so they appear as linear, right, in Lagrangian. So for them we introduce also parity, and for photon, parity is -1, so we introduce it in this way, reflecting this change of vectorial components of the parity. So we introduce transformations. Now we can check invariance. Okay? So you can check that electromagnetic interactions are invariant with respect to P transformations. So electromagnetic interaction, let me write invariance. Under P transformations, Lagrangian of electromagnetic interactions is charge, electric charge, psi, gamma mu psi, and then vector field. and we make summation over mu, right? So what happens is that the current, which is 4-component, and this field, electromagnetic field, which is 4-component vector, they transform in the same way. And therefore, this product doesn't change the sign, right? So 0 components, they do not change. And then vectorial components both change the sign, both this current and vectorial components of electromagnetic field. So, quantum electrodynamics is invariant. The same is for QCD, so, because in the case of QCD we have Lagrangian of interaction of quarks with gluon fields. And here let me put indices alpha, beta, and also index mu here. But again, it has the structure current times vector field. And for gluonic field, we introduce the same parity as for photon, for vector fields. And therefore, this also is invariant under P transformations. Okay? So both electrodynamics and both electromagnetic interactions and QCD are invariant with respect to P transformation. So in general, if you have structure of your interactions as current times vector field, it is invariant with respect to P transformations. Okay? So, for time being, we discussed these transformations at classical level, right? Now let me do this at quantum level. So here we have the transformations of the fields. F go to, and this equals P, operator of P transformation, field P minus 1. To match classical analysis, what we did before, we are saying that acting of operator P on the field produces for us this eta P multiplied by F minus X and T. So we can write that P F P minus 1 equals eta F. Now, this is operator expression, so everything is here operators, and let us act this on vacuum state. What we will get then is, and we take into account if vacuum is invariant, so let's say that, suppose vacuum is invariant, then what we will get is the following. P, let me write and then I will explain, equals eta P F. So, this will give me Fp, right? Now, acting on vacuum of this part, that, since vacuum is invariant, will give me again the vacuum. And then F acting on vacuum gives me this expression. So that equation, when I'm acting by this on the state on the vacuum, will give me this expression. Right? Or do you need to have more explanations? No problem. So So I multiply both left and right parts on the vacuum, and then I'm getting this expression. Provided that vacuum is invariant at P minus 1 acting on vacuum gives me a vacuum again. So here explicitly, because here everything are operators, P is operator, and therefore we see from this equation that eta P is eigenvalue of operator P in the state F. Now, if Hamiltonian is invariant under P, what we conclude, this means that P is commuting with Hamiltonian. In this case, eta P is conserved quantum number. So let me introduce to use this conservation of parity, introduce parity for the system of particles. Suppose we have state made of several fields. Let me do parity of system of particles. And this state is created by acting by operators F1, Fn onto vacuum state. So how this state is transformed under P? We can write this in the following way: Fp, F1, and then what we are doing, we are kind of inserting here P minus 1P, which is unit, in between of each of the fields. Then what we will get is P acting on F1, P minus 1, P F2, P minus 1, and I will have here in the end Pn F and I will put here P minus 1, sorry, this is n is here, 0. And I can do this if my vacuum is invariant under P. So now each of the fields here is surrounded by this P minus 1, and by definition this is eta P1, F1, eta P2, F2, eta Pn, Fn 0, and that equals eta P1 times eta P2 eta Pn and our F1 Fn. So the total parity of our state equals the product of eta Pi over all fields which are in the system. So this means that parity is a multiplicative quantum number. And so if we have the system of n particles, then total parity, what we call intrinsic parity, is given by the product of parities of individual particles. So we are saying this is intrinsic parity for the following reason. So the point is that we have the system of the particles which may be in some orbital motion. So they're moving around each other. And under reflection of coordinates, also the wave function which describes this motion, relative motion of these particles in configuration space, also change the sign. So in the case of, for instance, two particles, A and B, under P transformation they change the sign. So they change the order. Here it will be B and here it will be A. And under this transformation, the wave function which describes motion of these two particles may change the sign. So that psi, and suppose they are in orbital motion, which is described by total angular momentum L. So when it changes the sign, then that actually produces additional minus sign in the power L. Right? And this will be psi L. Remember quantum mechanics. So if you have a system of two particles and you change coordinates, and then the wave function may acquire additional sign, or it acquires the factor which is given by -1 in the power L, where L is the orbital momentum. So it is very important that you will see, because in this way we have determined the parities of different particles, that orbital parity turns out to be entangled with intrinsic parity. And really total parity of the system, which includes both intrinsic and orbital parities, is given by product of -1 L and then at the 1 at the n. So under this reflection, both the individual wave functions of particles in our system may change the sign or acquire this parity factor, and also due to orbital motion, we change the wave function in coordinate space of this motion, of the wave functions. Okay. Now let me say a little bit more about parity conservation. Okay, parity conservation. And this is important because conservation is applied to total parity, which includes also this factor. So you cannot apply just for this intrinsic part. So you need to consider total parity. And what is conserved as a consequence of, say, symmetry is total parity. So you need also to take into account orbital motion. Let me say a few words about parity conservation. Or in general, conservation of what we call discrete symmetries. So the symmetry which is associated with parity is discrete in the sense that the change is plus or minus 1. Right? So that's kind of, and the symmetry and this quantum number is multiplicative for this case, the conservation is proven in a slightly different way as it was before. So before, what I was using, that Q is Hermitian operator, remember? And in this case, the transformation which is given by exponent I Q alpha, that will be unitary. So this exponent is unitary if this is Hermitian. I think you have studied this, right? So now, in the case of parity, I do not need to have any exponential stuff. So which means that P itself is, so let me check that first, right, and then I will comment. So let me try F, final state, Hamiltonian, I, and that is given by the following. We insert here P minus 1P, and here P minus 1P, and this is Hermitian. Now, it's itself Hermitian, in contrast to this transformation when Hermitian part is sitting here. And therefore, I can write this as F P dagger P H P dagger P I. And so that will give me the following. This will give me eta F. Now, invariance give me that this is Hamiltonian. And this will give me eta I, initial state. And this is F, eta final state. So eventually what I will get here, eta F multiplied by eta I. And here is F, I, H, and I. And I started from this. This means that eta F multiplied by eta I should be 1. Right? Because this is the same line. And since these quantities take either plus or minus 1 values, that is equivalent that eta F equals eta I, which expresses conservation of parity. And I want to still today to say two things before I will finish. As we have this general consideration before, parity leads to certain equalities of matrix elements. So not only to conservation, but also equalities of the matrix elements. And so if you have matrix element between the state, which is characterized by a momentum Pf and lambda F is total helicity, and then we have S operator, and here is P initial, lambda initial. These are helicity. As a consequence of P conservation, I will get that this matrix element equals to matrix element when I change the sign of these quantities. But even more interesting consequences I will discuss a bit later. So I can change the sign of the momenta and the helicities, and I will get the same expression. And finally, once I discuss this total parity issue, let me briefly explain how the parity of Pine has been established. This is extremely important because you need to establish at least parity for one particle, but then you can use conservation of parity in different reactions due to strong interactions to find out what are parities of other particles. Okay? So very briefly, because in the previous years, actually, not even last year, but maybe 10 years ago, I explained this really beautiful and interesting and rich by of physics of way people measure the parity of pi. But today I'll just give you a brief explanation. To establish parity, experimentalists use two things: conservation of total parity in the strong interaction process, and second, this entangling of intrinsic parities and orbital parity. So that at the total is some minus 1L, and at the intrinsic. The process which experimentalists use was pi minus scattering on deuteron with final state which consists of two neutrons. Essential observation was that this process is not forbidden. It proceeds with the rate which is expected according to strong interactions. So observation is rate as in strong interactions, and there is not any additional suppression. The process proceeds in two phases. First phase is formation of pi atom. Due to electromagnetic interactions. So, what happens is the following: you scatter pi on deuterons, pi emits photons and sit onto orbit forming atom, where instead of electron you have pi minus and then proton, and then deuteron. So interesting, right? Pi is living 10 to the minus 8 seconds. And this is enormously long time actually, because electromagnetic processes characterized by lifetime, by time 10 to the minus 16, 10 to the minus 17 seconds, and therefore this system has a time really to emit photons and to form atom, and this atom lives very long time. Okay. The second phase. So and the pi is after emission of gammas in S state. This is important. And with orbital motion, momentum 0. So it's on the lowest, it sits down in the lowest state. So it forms the atom. And then the second phase is capture of pi by deuteron, and this is due to strong interactions. due to strong interaction. So what happens is that you have deuteron, fine rotating around, moving around the deuteron, and then pion is captured and two neutrons are produced, and of course they do not form any composite state, they just go apart each other. So that's initial state and this is final state. So in this initial state, because parity of deuteron is 1, so there is no intrinsic parity, we do not introduce for deuteron, and the orbital motion is 0, and therefore the parity of initial state is given by parity of pion. And here in the final state, the parity of final state is given by -1 and this orbital motion of two neutrons. So therefore we conclude that parity of pion is given by -1 and this orbital momentum of two neutrons. So in this way we connected intrinsic parity of pion with orbital motion of two neutrons. You can measure this, and you can actually find this using conservation of angular momentum. So here we use conservation of parity, right? So here is P conservation, or this is P conservation. Okay? Now we can use conservation of angular momentum and Pauli principle. Since we have two identical particles in final state, and therefore their wave function should be antisymmetric under permutations. Okay? So I will not present this analysis. But what has been found that the parity of final state is -1, so L and N is 1, and therefore parity of pion should be -1. Okay? And then one can use other strongly interacting processes due to strong interactions to establish the parities of other particles using conservation of parity and knowing parity of pion. Okay, questions? Yeah.
We know that because we say that the two neutrons should have the same intrinsic parity. Because of that,
it doesn't matter. Neutron is fermion, right? Mm-hmm. And for fermions, we do not introduce parity. Again, even here, you have two neutrons, and therefore you will have square of these parities, right? So it doesn't matter. Mm-hmm. And this usually happens all the time. So we do not introduce intrinsic parity of fermions. So interesting physics, right? I saw people. It's easy here theoretically, to introduce this wave function changes the sign, or using these properties, states with definite angular momentum, but not able to measure. Also, people measure it independently. Pi 0, parity of pi 0. Also, it is clear because pi 0 is in the same multiplier with pi plus and pi minus, the parity should be the same. However, they measured this independently because pi 0 decays into two photons, right? And then you need to find again this orbital motion of two photons. And for this, you need to measure polarization of photons. So measuring polarization of photons in decay of pi 0 into two photons, you can also find what is the parity of pi 0. And it was found is -1. Okay? Some more questions?
It usually they measure this angular distribution. Is it like that, or that's to try and spin?
So what is interesting that even no need to measure any further things, because it is enough to say that there is no any additional suppression. So just use here conservation of angular momentum and Pauli principle, and then do kind of analysis of different possibilities. One can conclude that it should be minus 1. Interestingly, just from the fact that this process occurs without any additional suppression, you can establish what is the parity and what is orbital momentum. So already Pauli principle immediately tells you what in which states orbital states can be neutron, right? And then you use conservation of angular momentum. So on the top of parity, you can use that angular momentum in initial state and in final state are the same. So you know what is the angular momentum of initial state. So just using the combination of these two relations, you can find uniquely what is this orbital moment of two neutrons. Okay? So we'll continue tomorrow. Parity violation also.